Hello, hello, hello everyone, and welcome to the Ben's Chem Videos Friday Night Live Stream. Here we are doing our fifth and final volume on chemical kinetics. We have done 4 volumes thus far, and it is the fifth and final one. If you want to find any of the other volumes, if you're new to the stream, there is a playlist called Chemical Kinetics Live Streams. You can find that in the description of this video, and that will take you to all of those volumes. So it's good to be back. I originally intended to do this live stream last Friday. However, last Friday I underwent surgery, and I wasn't sure whether or not I was going to be capable of doing a live stream. Turns out I was incapable of doing a live stream last Friday night. I went home, passed out, woke up at like 7 p.m. with nothing prepared, so I decided probably best not to do one. So if you want to hear more about that, if you want to talk more about that, maybe we could do so after the educational part of the live stream. But with that, let's see, do I have any other announcements? Yep. Well, I guess one thing I'll say is that I'm working to try to get rid of all this computer fan noise. I know my computer fan is pretty loud, so I'm going to try to figure out how to adjust my volume levels or maybe upgrade my microphone or do something to reduce that noise. Other than that, so yeah, that's pretty much it. Feel free to participate with your thoughts, comments, concerns, questions, whatever, in the chat, or even better, call in via Discord. The call-in link is in the description. You can call into the show, and you can ask a question, talk about whatever. It is highly encouraged. So without further ado, let's go ahead and get into the educational stuff. So this is Chemical Kinetics, Volume 5. Here we go. If I can, yep, there it is. All right, so the way I always like to start these live streams is to simply review all the material that we learned from the last live stream. Last live stream, of course, being Volume 4. And Volume 4 was all about the topic of reaction mechanisms. Reaction mechanism, of course, is the sequence of steps by which an overall reaction occurs. And those steps are also called elementary steps. I usually just call them steps because it's easier to say. And so the reaction mechanism tells the story of how the reactants become products, right? If you look at a balanced chemical equation, all that tells you is what you started with and what you end up with. It doesn't tell you how the reactants became products. That's what reaction mechanisms do. And one of the important aspects of reaction mechanisms that you would never see in a balanced chemical equation are reaction intermediates, which are substances that are produced in one step of a mechanism and consumed in another. So for instance, this is the reaction that we looked at right here, where in the first, this is a 2-step reaction. The first step, you have NO2 reacting with Cl2 to become ClNO2 and just plain old Cl. And then if you look closely, you'll see that that Cl is consumed in the following step of the reaction. So it doesn't appear anywhere in the balanced chemical equation, but nonetheless, it plays a very, very important role in the overall reaction. So that's what a reaction intermediate is. So I'm pretty sure you get the idea. So we can move forward. So we talked about reaction intermediates. We talked about how to how we understood the rate laws for elementary steps, and we understood that in the context of molecularity, which is simply the number of reactant particles that are involved in a given elementary step. We have unimolecular, which is 1 particle, bimolecular, which is 2 particles colliding together, and then there's a third case called termolecular, where you have 3 particles colliding together, but it's pretty rare given that the probability of 3 particles colliding at the exact same time is very, very low. So this is just a quick little table to sum up all of the possibilities and all the rate laws associated with unimolecular, bimolecular, and termolecular elementary steps. Unimolecular obviously is the easiest. So if you have 1 molecule decomposing into products, the rate law for that is simply the rate constant times the concentration of that particle. If you have a bimolecular process, there's 2 possibilities where you have either 2 of the same particle or 2 different particles. If you have 2 of the same particle, it's going to be the rate constant times the concentration of that particle squared. And if you have 2 different particles, it's simply going to be the rate constant times the concentration of each of those individual particles. And then also the 3 possibilities for termolecular elementary steps are shown below. Got a message in the chat from Lakshmi Praveen, says hi. Hello, very nice to see you. I don't recognize your name, but I'm also not the best at remembering names. So if you're new, welcome. And if you are returning, then welcome back. I really, really appreciate your being here. And that goes for all of you who are watching. So, okay, so that's molecularity. We talked about that. To continue our review from the last live stream, we talked about the concept of a rate limiting step, also called a rate determining step. Those are synonyms, and that is a very, very important concept because the rate limiting step, that's the slowest step of the chemical reaction that limits or determines how fast the reaction can proceed. And this is analogous to, say, the narrowest section of a highway, right? The traffic can only flow as fast as the narrowest, thinnest section of the highway will allow. The logic continues with chemical reactions, right? The chemical reaction will only proceed as fast as the rate limiting step will allow. So to give you an idea of this, this is another thing we looked at. This is a energy versus reaction progress diagram for a two-step chemical reaction in which the first step, the first elementary step in that mechanism is the rate limiting step. And the reason why some elementary steps are slower than others is because they have higher activation energies. So the activation energy, of course, that is the amount of energy that must be put into the system in order for the reaction to proceed. So even in an exothermic or energetically downhill reaction such as the one shown here, you still have to put some energy in to get the reaction to go, and that's called the activation energy. And the maximum in energy from one elementary step to another, that's called the transition state. Transition states, you can think of them as like the reactant particles are kind of breaking and the product particles are kind of forming, things like that. So that's the transition state. I got another message from Nicole S. It says, "Hey, Ben." Hello, Nicole. I don't recognize your name, so welcome if you're new, and if you are returning, welcome back. Thank you for being here. I truly, truly appreciate it. Okay, so as I was saying before, the reason why some elementary steps are slower than others is because they have larger activation barriers. The larger the activation barrier, the slower the reaction, which follows according to the Arrhenius equation, which is something that we discussed, I believe, in volume 3. So if you're unfamiliar with that, I highly suggest you check out volume 3. So there we go. All right. The other thing we talked about, which is very, very important, was the requirements for a valid mechanism. So remember, reaction mechanisms, they are not proven, they can only be validated, right? Because you can't like interview molecules to figure out where they've been. You can only sort of probe them experimentally to deduce what the mechanism probably is, but they're never actually proven. They're either valid or invalid, right? So the two requirements for a mechanism to be valid are, number one, the sum of the elementary steps must equate to the overall chemical reaction equation. That's requirement number one. And requirement number two is that the rate law predicted by the mechanism must be consistent with the experimentally observed rate law, which basically means that you can't have any reaction intermediates in the overall equation for your rate law. And I hope I'm not losing you right now. If I am, then I would highly suggest checking out volume 4. But that is nevertheless the second requirement for a valid mechanism. And then the last thing we did was to go through a couple of practice problems where we predicted the rate laws for an overall chemical reaction using a proposed mechanism. Okay, so that sums up the review for volume 4. Thank you for staying with me. I hope I haven't driven anybody away, but for those of you who are still here, thank you for staying with me. So let's get on to today's topic. Today is going to be a fairly short stream because we only have a little bit material left to cover with kinetics, but it's a pretty interesting and pretty important topic nonetheless, and that is the topic of catalysis. So far in this Chemical Kinetics live streams series, we've talked about a few ways by which the rate of a chemical reaction can be controlled. Usually we like to increase reaction rates, right? Because chemists, we don't have all day. We want the reaction to proceed as fast as possible. So we talked about how the rate of a chemical reaction can be increased by manipulating concentration, right? Assuming it's not a zero order reaction. Most reactions are not zero order. The rates of the reactions mostly do depend on concentration. But we're limited, right? There's a limit to how concentrated we can make a reaction mixture. We can't just infinitely concentrate the reactants. So that's quite limited. And then there's temperature, right? When we talked about the Arrhenius equation, we understood that increasing the temperature increases the reaction rate because it increases the rate constant. And there's also limits to how hot you can get the reaction mixture too, because if you get it too hot, well, then you might start getting some undesired reactions. The molecules that you want to keep intact might start breaking apart, and that's no good. So there's a third way by which we can increase the rate of the reaction, and that is by using what's called a catalyst. So you've probably heard the term catalyst before. You know, like let's say, I used to live in Orlando, so we could say when Dwight Howard was drafted by the Orlando Magic, he was the catalyst that they needed to get to the Eastern Conference Finals, right? Something like that. So there's a lot of colloquial usage of the term catalyst, but catalyst has a very, very real and very, very literal definition, and that's what we're going to talk about in today's lesson. So a catalyst is a substance that increases the rate of a chemical reaction without being consumed by the reaction. A substance that increases a reaction rate without being consumed by the reaction. So to explain how this works, let's consider a particular chemical reaction. So the example that we're going to look at in this one is the non-catalytic destruction of ozone, whose chemical equation is shown right here. Got another message in the chat from Jacob Halber. Says you should do another sulfur hexafluoride video. You're right. I should. I want to wait for the mask mandates and stuff like that to be lifted, because I think in order to capture people's facial expressions and reactions, I think it's better when they're not wearing masks. So I'm waiting for that before I can do another one, but thank you for your feedback. So back to the topic of catalysis. So this equation is what's called the non-catalytic destruction of ozone, right? So ozone, O3, is a component of the upper atmosphere, right? And it gets destroyed naturally according to this equation, where you have, and this is a one-step mechanism where you have a molecule of O3 colliding with an individual oxygen atom to produce two O2 molecules. So it occurs via one elementary step. And you might think, oh no, the ozone is being destroyed by this reaction. Well, yeah, it is, but it's occurring naturally. And this particular reaction is slow because it has a fairly high activation energy, right? Now, imagine that there's a catalyst introduced to this reaction, which happens a lot because of man-made chlorofluorocarbons, which I'm not trying to go on some environmental rant or anything like that, but this is just an example of one reaction that's catalyzed by man-made chlorofluorocarbons. So the destruction of ozone can actually be sped up and catalyzed by chlorine. And the chlorine atoms, again, they come from chlorofluorocarbons. So the way that chlorine catalyzed destruction of ozone works is by a two-step process, right? In the first step, you have a chlorine atom colliding with an ozone molecule to produce ClO and an O2 molecule. And then in the second step, you have the ClO molecule that was produced by the first step colliding with an oxygen atom to yield one chlorine atom and one oxygen atom. So notice that the initial definition of catalyst was something that increases the rate of a chemical reaction without being consumed, right? So in this case, the chlorine, that's the catalyst, right? Now notice that the chlorine is introduced as a reactant in the first step, and it's a product of the second step, right? So it's regenerated by this mechanism. So it's not actually consumed. It's consumed for a very short period of time in that first step, but it's reproduced in the second step. So this mechanism, this chlorine catalyzed destruction of ozone, occurs via two elementary steps rather than one. And each of those two steps have low activation energies. Now you might be thinking, how does adding a second step to a mechanism gonna speed up a reaction? It's kind of counterintuitive. You would think adding a second step would actually slow things down, but that's actually not the case, because remember, it's not about how many steps there are, it's about how fast your slowest step is, how fast your rate limiting step is. And so if we look at this, just to show you, for instance, if we cancel out the catalyst and we cancel out the ClO intermediate, notice that if we add these two reactions or these two elementary steps together, we do indeed get the same reaction that we had before, right? The one that occurred in one step where you have O3 plus O yields 2O2, right? So just wanted to make sure I put that in there, that they're both the same reaction. They're just occurring by two different mechanisms, right? And so if we look at a diagram of this is another one of those energy versus reaction progress diagrams. So the graph shown in blue here, this represents the uncatalyzed pathway, the single step mechanism that occurs naturally, right? And it has a high activation energy because this little hump right here is really, really high up, right? And notice that there's one of them. There's one of those peaks right here, right? Which makes sense because there's one step, right? And in red, this represents the catalyzed pathway where we have two steps, right? Two humps, two local maxima, right? Got another message in the chat. Says, Ben, will you make video on amines, biomolecules, P-block, coordination compounds, and haloalkenes, amines mechanism for next time videos? Wow, that's a lot of material. No guarantees, but I will certainly consider it, man. Thank you very much for the suggestion. And that goes for everybody in here. Any suggestions that you might have, any feedback that you might have, I wholeheartedly appreciate it. So thank you very much. And also, if you are feeling super generous, you are more than welcome to send a super chat. I do have them enabled. Just throwing that out there. Okay, so back to the lesson. So notice that we have, like I said, these two different pathways here. The uncatalyzed pathway that has a very high activation energy for its rate limiting step, which is the only step, and the catalyzed pathway, which even though it occurs via two steps, each of those two steps has a very low activation barrier. And so therefore the catalyzed pathway is going to be the faster reaction. So in this case, the reaction that is being catalyzed is an unfavorable one. It's one that we really don't want to happen because the ozone layer is important because it protects us from the damage of ultraviolet light. But other times, oftentimes, we actually intentionally use catalysts to speed up reactions that we do want to occur. We speed up reactions that we do want to go faster. So for instance, one of those such reactions is the catalytic converter in your automobile. So you've probably heard the term catalytic converter before, but you may or may not have given much thought to what that term actually means or how it works. So the catalytic converter is a component of your vehicle that's connected to your exhaust, right? So your engine, it burns up some fuel, and then the fuel turns into exhaust, and that exits your vehicle, right? Now, in the engine of a car, there's combustion of the fuel, but the combustion is generally not complete. There are plenty of incomplete combustion products. It's not a completely efficient process, right? And so there's a couple of things that come out of the car that are really nasty, like carbon monoxide, like nitric oxide, like nitrogen dioxide, fragments of the fuel that just didn't get burned, all of those kind of things that if they were released into the atmosphere, well, they're not so good, right? They're not so good for the environment, right? And so the way that the catalytic converter works is it has this high surface area ceramic structure, and within that high surface area ceramic structure, let's try saying that 10 times fast, you have these metal catalysts. You have platinum, palladium, rhodium, little bits of that metal, right? And that metal catalyzes the reaction of these nasty materials that we don't want into the atmosphere to make things like water, which is harmless, right? I mean, we drink it. It makes up over half of our bodies by mass, right? Nitrogen gas is very inert. It's pretty much harmless. It makes up 78% of the air that we breathe. So nitrogen is infinitely preferable than something like nitric oxide or nitrogen dioxide, which are both toxic, and CO2. And, you know, obviously it's debatable about how good CO2 is for the atmosphere. It is a greenhouse gas, although plants seem to like it. They consume CO2. But CO2 is definitely a lesser evil than just plain CO, right? CO2, carbon dioxide, much better to have in your atmosphere than carbon monoxide. So the catalytic converter takes advantage of catalysis to convert things that are bad to things that are either good or not as bad. So that's how your catalytic converter works. And there's another sort of thing with catalysis that I wanted to tell you guys about. Now, this is from personal experience. So at my last job, not the job where I'm working now, but my last job, I did a lot of work with inert atmosphere chemistry, like a lot of, I worked with a lot of air sensitive and moisture sensitive materials, like things that if you open the container in the presence of air, it would ignite or it would ruin the material. So pretty dangerous stuff. And one efficient way to handle these kinds of things is by using a glove box or an anaerobic chamber. And this is actually the kind right here that I used to use every single day. And as you can imagine, it can be pretty difficult to reach with those gloves and try to do delicate work that way. But one of the things that I wanted to bring to your attention is this thing right here. This thing, it's called the heater, or the blower, as it's often called. So the way that this works, right? So obviously you have this chamber, and you want to keep the oxygen out of it, right? Because oxygen is the component of the air that reacts with air-sensitive materials, right? So you have this unit here, and what it does is it takes the atmosphere that's inside the glove box and it sucks it through the bottom and it pushes it up through the top, right? And at the top, notice that there's this metal thing. This is a palladium canister. So it's this metal canister that has a bunch of little palladium pellets in it, right? And what that does is it catalyzes the reaction of hydrogen with oxygen to produce water. So whenever you are filling this chamber with gas, the gas that you fill it with is part of it, most of it is argon, but the rest of it is hydrogen. So you intentionally introduce hydrogen gas in here to react with any oxygen that leaks in just incidentally, because no matter how hard you try, there's definitely going to be some oxygen that leaks in. So that oxygen reacts with the hydrogen that you already have in there, and it's catalyzed by this palladium canister in here, and it produces water. Now, it's also not good to have water in your glove box either, but that's why there's this thing up here. This is called a drying train. It's basically like these 3 canisters. You push a button, and it cycles the atmosphere through the drying train, and it's packed with molecular sieves that trap the water. So it's pretty cool stuff. It's pretty cool stuff. It's a very elegant solution to the problem of air and moisture contamination within an inert atmosphere anaerobic glove box. So just another example of catalysis doing work for us. Now, one thing I wanted to touch on is 2 different types of catalysis, which are homogeneous and heterogeneous. So and these are pretty straightforward. A homogeneous catalyst is a catalyst that exists in the same phase as the reactants. And then on the flip side, you have heterogeneous catalysts, which exist in a phase that is different from the reactants, right? So an example of homogeneous catalyst, that would be like the chlorine that gets introduced into the atmosphere that catalyzes the destruction of ozone, right? Because the chlorine is a gas, the ozone is also a gas. They're the same phase, right? Heterogeneous catalyst, that would be like the solid bits of metal that are suspended in that ceramic structure in the catalytic converter of your automobile. So just as a little diagram here, we can see these 2 different types of catalysts here. Homogeneous catalyst, as I said before, is the same phase as your reactant particles. In this case, they're both gases. And then in the wow, I just realized that this should be hetero, not homo. You know what? I'm just going to fix that right now. Hang on. It's bugging me. Didn't have a whole lot of time to proofread this. There we go. All right. Good as new. So, homogeneous catalyst, same phase. The catalyst is in the same phase as the reactants. A heterogeneous catalyst, in this case, we have like a solid catalyst, like with the palladium or rhodium or whatever, catalytic converter, different phase of matter as your reactant particles. So, by the way, if anybody has any feedback or questions they'd like to ask, please feel free to drop them in the chat, or even better, call into the show. And if you find this stream valuable, I would certainly appreciate if you throw a like at this video. So, all right. So the last thing that I wanted to talk about, just as I suspected, the stream is going pretty quickly, so are enzymes, which are catalysts within organisms. So if you think about all the tools that chemists have available in the lab to speed up chemical reactions, like increasing temperatures really high, increasing pressures, increasing concentration, things like that. A lot of these techniques that we use in the laboratory are not available to biological organisms because high temperatures and high pressures and stuff like that would damage living cells. So they don't have those, organisms don't have those methods available. But what they do have are these things called enzymes. You've probably heard the term enzymes before. But basically what an enzyme is it is a protein. Now, proteins are these biological molecules that are made up of very, very long chains of amino acids in a particular sequence that bend and fold and form all these intricate, elaborate shapes. So an enzyme is a protein that acts as a catalyst. So, and the way that it acts as a catalyst is the enzyme has a very specific region located in it, which is called the active site, which is shown here. And that active site is basically like a lock, and the molecule that is going to undergo the reaction, which we call the substrate, is like a key. So the substrate fits into the active site of an enzyme, similar to a key fitting into a lock, right? And because of the way that the enzyme binds the substrate, it binds the substrate in a way that that allows for, let's say, an ideal reaction where the activation energy is much, much lower, and that substrate reacts to form products in a way that is much faster than if it were left to react on its own without the enzyme. Jacob says biochemistry at its finest. Yeah, definitely. I mean, this is a very simplified, watered down version of it. It certainly gets much, much more complicated than that if you go on to actually study biochemistry. Admittedly, biochemistry was one of my least favorite chemistry topics to study. I don't know why. I think it's because it just required like a lot of memorization. And I just don't like memorizing things. So, all right, guys, that, believe it or not, is it for the educational part of this live stream. Thank you so much for watching. I really, really do appreciate it. Again, I can't hammer this point enough. If you found this video valuable or not, I want to hear your feedback. Please let me know what's good. Let me know what sucks. I've been looking at my numbers lately, and they are a little discouraging, to put it mildly, and I'm doing everything that I can to try to revive my dead channel and bring it back to life. But one thing that really helps with that is your feedback. So leave your feedback. Like I said before, if you find the video valuable, slap a like on it. If you're feeling really generous, consider sending a super chat. Help out the show. Be much appreciated. So yeah, that's it. And thanks again for watching.